Have Andrea Colledan talking to us about secret width estimation via effect typing and linear dependency.
All right. Hello. Today I'm presenting a joint work with Ugo del Lago about the resource estimation of quantum circuit description languages. So just a little bit of refresher. What is a quantum circuit description language, or QCDL? It's basically a paradigm of quantum programming in which programs are actually classical. They execute on traditional machines, and they produce a description of a quantum computation as a result, usually in the form of a circuit. So we have quantum primitives, quantum operations, but instead of carrying them out, we basically buffer them to some internal representation and return that representation in the form of a circuit, and alongside the result of the computation. And so then we can take those circuits and combine them or manipulate them and describe more complex circuits, or we can just send them to quantum hardware for direct execution. And this is a paradigm that's been adopted by many mainstream quantum programming languages in the past decade, such as, for example, Qiskit or Quipper, which is a quantum circuit description language embedded in Haskell. So, for example, in Quipper, I can write the following function, which does some quantum operations, and then when I apply it to an adequate argument, I get the circuit as a result, together with two references to the output qubits bits of the circuit. And the good news about this is that because these languages are essentially classical languages, we can leverage the expressive power of modern, general purpose languages such as Python, Haskell, you name it, to do some very complex circuit construction and build very complex, very complex quantum algorithms that, translated to circuits, mean millions of qubits and trillions of operations applied to them. And the bad news is that real-world quantum computers at the moment are nowhere near this scale. They're very small and unreliable, and this means that it's very, very easy to write programs in QCDLs which vastly outperform quantum architectures, even on very modest input sizes. And so, for this reason, in this scenario, we thought that verifying the resource consumption of programs written in these QCDLs was a very worthwhile pursuit, and specifically we wanted to tackle the number of qubits required by a computation. So in this context, the width of the circuits produced by a program in a QCDL. And in this sense, our contribution has been a paradigmatic quantum circuit description language in the tradition of the Proto-Quipper language family, endowed with a refinement type and effect system that allows us to derive concrete upper bounds on the width of the circuits produced by a program. And these bounds are parametric, and we'll see in the size of the input of the program, and we'll see in a second why this is relevant. And together with the usual proof of correctness that tells us that our analysis is in fact sound with respect to the circuit building semantics of the language. Okay, so let's have a look at this language. This language is our language, which we call Proto-Quipper-R, is very strongly inspired by Proto-Quipper-M. At its very core, this is a effectful lambda calculus. So we have a distinction between terms and values. Return turns a value into a trivial computation, let sequences computations, and so on. And the side effect of this lambda calculus is precisely that of building a circuit. So circuit construction happens in a way behind the scenes as a side effect of a computation. And we have, of course, bespoke data types and constructs to perform this circuit manipulation. So to start, what you see written as L is a reference to a free wire in the underlying quantum circuit, which we call a label. what you see highlighted now is a boxed circuit. So I just finished saying that circuit construction happens as a side effect, but we can also have a way of turning the circuits that we build as a side effect into data for reuse later on, and for composing simpler circuits into more complex computations. And this is also the kind of term that encodes primitive operations in the language. So we assume to have one such term for every primitive operation that we want to carry out. And the basic the most fundamental construct of the language is the apply construct. Basically, apply VW appends a boxed circuit V representing some general quantum operation to the wires identified by W in the underlying circuit. So as a little bit of example of how circuit building, oh yeah, and we also have like a limited form of recursion via hard-coded fault operator. Okay, so to have an idea of how circuit building happens and what kind of considerations we have to take into account when we analyze width, let's consider the following program. It takes as input a qubit. It applies the initialize operation init1 to the circuit, meaning that it basically emits an initialize operation to the circuit. Then it applies an operation to the two qubits that we have, and then discards the auxiliary qubit that was just initialized. And so when we run this, we get something like this, where the circuit is precisely encodes the operations that we carried out in the function. And it's very easy to see that the circuit has width 2, because we have one input qubit, and then we initialize an additional qubit, and then it's very easy to conclude that the overall width is 2. But then we might want to take this function and apply it twice to the same input, getting a circuit that looks like this. And in this case, we have one input qubit and 2 initializations, but still the width is 2, because we perform some, we discard the auxiliary qubit before we initialize the new one, and so we can do some form of recycling. So first of all, we want our analysis to be able to capture reuse of discarded wires. But then these examples are nice, but they're not really what we would call a quantum algorithm, because usually when we talk about quantum algorithms, we mean circuit families that are indexed on the size of the input. We can write this in the language. For example, Hadamard n is a function from list of qubits to from list of qubit to list of qubit, and basically what it produces is the following circuit that just applies the Hadamard gate to all of its inputs. And this is like a pre-processing stage in many quantum algorithms, as you will know. And it's very easy to see that there is no way to give a fixed width upper bound to this circuit, because the width of this circuit is n, where n is the size of the list in input. So not only we want to be able to track reuse, we also want to be able to track this form of dependency, which means that our bounds ought to be parametric, because otherwise we wouldn't be able to capture. We would only be able to analyze single circuits, and that's fairly uninteresting. Okay, so let's see how we can use types to actually do this kind of analysis. We start from the basic, almost universal Proto-Quipper types, which form a linear nonlinear type system in which qubits and bits and functions have linear types. Circ is the type of circuits seen as data. And we extend this kind of type system, which does nothing in terms of resource analysis, in 2 directions. One direction is that of refining types in the style of the Lago and Gabardi. And what we do basically is take key types and annotate them with indices, which are just arithmetic expressions on natural numbers and variables. So if you look at the grammar, this is a natural number, this is a index variable, which tell us some interesting information about the elements of this type. So for example, circ ITU is the type of boxed circuits of width at most I, with input T and output U. List I of A contains lists of exactly I elements. And the most convoluted annotation maybe is that of functions. Functions are annotated with two indices. The first one tells us what the upper bound to the width of the circuit that the function produces once we apply it to an input of type A. And the second one tells us exactly how many wires the corresponding closure contains from the outside environment. So that's a bit oddly worded, but basically how many wires the function captures from the environment. And we'll see in a second why this is relevant. And the second ingredient in our analysis is effect typing. So our type system revolves around a typing judgment of this form, which reads for all index variables in theta, under typing context gamma, which gives types to variables, and label context q, which gives types to the wires in the underlying circuit. M is given type A and builds a circuit of width at most I. So in this case, I is still an index, but it's an effect annotation that tells us something about the side effect released by the program. We have a similar judgment for values, which however are effectless. And here the universal quantification over the index variables in theta allows us to regain some form of dependency. Because if we write something like this, we can basically express that the function Hallerman n that we saw earlier as type for all I from list I of qubit to list I of qubit, building a circuit of width at most I. Okay, so let's see some interesting rules of the system. Apply is the most basic rule. From the typing perspective, that's pretty straightforward. If we apply V of input type T and output type U to a value W of type T, we get a result of type U. From the circuit building perspective, what's happening here? So V is a box circuit, which means that there is an associated, a circuit object associated to it. Let's call it CV. And apply does nothing but basically turn that datum into a side effect. So the circuit that gets built is this one, and the inputs to this circuit are the wires that are contained in contexts gamma 2 and Q2, because these are the contexts under which we type W. And in this case, it's really easy to conclude what the overall width is, because we know by this annotation that V is a circuit of width at most I, so we conclude that apply VW builds a term of width at most, builds a circuit of width at most I. Let's make things slightly more complicated, or although it might not look like that. What is the effect notation of return V? So at first glance, okay, return V is a trivial computation, so we might conclude that it does nothing. So basically, it builds the empty circuit and it has width annotation 0. But that's not the case, because wire references in this language are values, and so V might contain many references to the wires in the underlying circuit. And so morally speaking, the circuit that's being built by return V is not the empty circuit, but rather the identity circuit on the wires contained in gamma and Q, under which V is typed. What is the width of the circuit? Well, the only way that we have to conclude something about the width of the circuit is to find out how many wires are contained in gamma and Q. And we denote this quantity with the hash symbol, which will read the wire count of gamma or Q or gamma and Q as a shorthand. And this is a central element of our type system. We obtain this quantity in a very easy way. In fact, we just traverse the typing context, look at the types that are mentioned in it, and derive from those types an estimate of how many wires are represented by that type. And that's fairly easy for most type, except for function types, because from a function type we cannot say anything about how many wires are inside the corresponding closure. So we have to keep track of this value explicitly in the second index j, which is precisely the wire count of this type. And this annotation is generated in the abstraction rule in a very similar way as it is generated in the return rule. All right, so one last example, the let rule. Type-wise, this is fairly standard. From the circuit building perspective, what is going on? Basically, M builds its own circuit, which we call Cm, and which by the premise we know is the width of Cm is bounded by I. Then this circuit has some outputs. Because of linearity, all those outputs must be bound to x of type A. And still, due to linearity, all these outputs containing x of type A must be taken as input by the circuit built by the second term n, which by premise has width at most j. So at this point, it might be natural to conclude, okay, we have like one thing of width I, one thing of width j. We are putting them together like in sequence. The overall width must be something like the maximum of I and j, right? There's a catch to that, because x of type A is not the only input to Cn. N is also typed under gamma 2 and Q2, which contain wires which must pass alongside Cm while we're building, morally speaking, must pass alongside Cm while it's getting built. And these wires have a width that adds up to the overall width of the left-hand side of the let. So the width of this left-hand side is actually I plus the wire count of gamma 2 and Q2, and the overall width of the let expression is the maximum of I plus the wire count of gamma 2, Q2, and j. And this is the last rule I'm showing you. I'll spare you the rule for fold, because no one deserves that on a Saturday morning. Let's talk well-typedness. Like in most other Proto-Quipper instances, it makes no sense to speak of the well-typedness of a program in isolation, because a program manipulates a circuit, and thus it must be paired with a circuit that provides the right kind of wires. So, well-typedness we write as such, and we read that configuration Cm, where C is a circuit, M is a term, is well-typed with input Q, output L, type A, and the effect notation I, that is with at most I, when C has the right signature and provides as outputs, as some of its outputs, the wires that are used to give type to M. So it's something that's illustrated in the figure. And okay, so what can we say about well-typed configurations? We model circuit building semantics through a big step evaluation relation that tells us that M evaluates to V, and in doing so, as a side effect, updates circuit C to circuit D. And what we can say about well-typed configurations is, well, subject reduction, that tells us that well-typed configurations stay well-typed when we evaluate them, but also, and most importantly, total correctness, which tells us that if a configuration is well-typed, then it evaluates to something, and in particular, M evaluates to V, and in doing so, as a side effect, it extends C with a subcircuit D, which has width at most I. So this tells us basically that the circuit that the term extends the underlying circuit with is bounded effectively by the effect notation that we derive through our type system. All right, so that's pretty much it. As further work, we are working on the implementation of the type checking procedure for this language. And we're also in parallel working on the notational semantics for the language, which is something that most Proto-Quipper incarnations have that we still do not have. And other than that, we would like to generalize this analysis to other kinds of resources, such as the gate count of the circuit, so its size, or the circuit depth of the circuit, or whatever. So that's pretty much it. Thank you for your attention.
Any questions?
Thanks for the talk. I can kind of see how you could generalize this to gate count. Mm-hmm. Still a very syntax-directed thing. I just need a track. When I put a gate, I increment something. Do you have some ideas about how you would do this for depth?
Yes, and it's very different actually, because we found that the only way to have a good estimate on depth was to keep the analysis at a very local level. So our idea is to basically take where are they? Well, basically the qubit and bit types and annotate them with indices that tell us basically, okay, this is a label, this is a wire reference of type qubit, and also the sub-circuit that's rooted in this label has a certain depth, and then try and compose this kind of local annotations, and in the end, only in the end conclude something global about the circuit. But still, this is still in the very early stages of exploration.
Thanks.
So the newest versions of Proto-Quipper, have both dependent and linear types in them, and it seems like the dependent types do a fairly good job of capturing the width of the circuit. So I was wondering, if you could talk a little bit about the difference, and B, whether or not you can integrate this with the newest Proto-Quipper.
Well, our original goal was to try and see if with Proto-Quipper-D we could do something similar, and in principle it looks like yes, it can be done. However, at some point we wondered whether it was possible to have some much more lightweight verification of this property, because it seemed that we were doing the same thing over and over again. Our idea is that because these are basically refinement types, we might be able to automatize a lot of the basically proof work that goes into proving that things match up correctly. So this was our main motivation for going in this direction. I don't know how we would go about integrating Proto-Quipper-D and this kind of more refinement type-oriented analysis.
Because specifically you don't want to deal with the complexity of Proto-Quipper-D.
Yes.
I see. Thank you.
Nice talks, thanks.
Thank you.
So, how tight are those estimates?
Well, we have no real formal result on how tight they are, but they seem quite tight. We haven't done much experimenting with very big quantum algorithms, but for example, we did manage to type check the quantum Fourier transform family of circuits, and in that case, the upper bound is exact. But then again, that's expectable because you don't have much recycling going on. On very simple examples, it is exact. We still have to find a counterexample to that, but we do believe that they exist.
So you have an implementation?
Yes.
Okay.
A very
prototype.
contrived
A prototype.
implementation
Yeah.
of a QFT, but yes.
Okay, thank you.
So my question was about recycling. I don't think you've shown any inference rule that showed recycling, or if you did, I didn't.
It's in a way it's implicit in the let rule, in the fact that we compose with a maximum.
Okay, no, fair enough.
That's implicitly assuming that we can reuse any wires that do not appear in the output signature of the first circuit. We can reuse in the second.
Makes sense. And I'm going to ask you the same question I asked about Bart. How would you keep track of which wires can be recycled?
That's a nice question. You mean basically having some actual constraints on when a wire can be recycled and when it cannot be recycled,
Yes.
right?
It doesn't have to be in a type system.
Okay. So basically, what happens is I don't think I know how to explain this very briefly because it's kind of an emergent property of the whole thing. But basically, what happens is when we discard something, and I maybe can find an example. No, it was here. When we discard something that has a width, but it doesn't have an output, because the discard operation basically outputs the unit value. And this together with the let rule that allows us to compose computations in sequence through the with combining effects with the maximum operation. Basically, that implicitly allows us to treat that that wire as a discarded wire, as opposed to a wire that must be kept alive in a way. Also, linearity plays a big role in this, because we cannot just forget about linear wires. We're obligated to do something with them, even though it's an op. We have to take them into account.
Thanks.
Thanks very much.